opportunity to speak here. So yes, as you said, the problem is quite old in its original form. So this is Euler's 36 officers problem. I'll give an introduction. And my goal in this talk is to explain all the terms in the title. What is the problem? What is meant by a quantum solution to this problem? And what is meant by infinitely many? Now it might seem surprising that I'll have to explain what is meant by infinitely many, but when you have quantum solutions, we'd like to know when two of them are regarded as equivalent or essentially the same solution, and so we need techniques for that, and that's one of the main things that goes into the proof of various things. So all of this is joint work with Suhail Radha, N. Ramadas and Arul Lakshminarayanan at IIT Madras, physicists at IIT Madras. And that picture down there, this picture is what is called a picture invariant, and this is one of the main techniques that we use to solve the problem. I'll say something more about picture invariants as we go in. Okay, so let's begin with a little bit of origins of this problem, Euler's 36 officer problem. So the date, it's roughly the late 1700s, and that's Catherine the Great of Russia. Euler was at her court during this time, and folklore has it that she asked him the following question. So the question is the following: there are 6 different regiments, each having 6 officers of different ranks, and we'd like to arrange these 36 officers in a 6 by 6 square grid, such that every row and column contains 1 officer from each regiment and also 1 officer of each rank. So this is just a puzzle problem, right? So if you like puzzles, then you can try and think about how one would solve a problem of this kind. Now when you think about this, the first thing you might try is, why 36? Why don't we do with, say, 3 by 3 where you have 9, or 4 by 4 where you have 16? So you can try this problem for any square. There's nothing particular about 36, but on the other hand, we will see that there is something particular about 36 a little later. Okay, yeah. So here is a solution to the 5 by 5 case of the problem. So where are the officers and where are the ranks and regiments and all that? So we think of chess pieces as representing the ranks of the officers, and colors as representing the different regiments. So there's a black one, there's a red one, so all of these are different regiments, and the king or the queen or the rook, they all represent ranks of these officers. And you can see that in this arrangement, each one occurs 5 times. So the king here occurs in all 5 colors, this queen occurs in all 5, this rook occurs in all 5. Each of the 5 occur in all 5 colors. That's one property. Further, every row and every column has each of the colors represented and each of the chess pieces represented. So if you look at this first row over here, it has all 5 colors and all 5 chess pieces, and that holds for all the 5 rows and all the 5 columns. So this is the kind of arrangement we want, but not for 5 by 5. We want the answer for 6 by 6. We want such an arrangement for 6 by 6. At least that was the problem that Euler dealt with. So the terms that are used nowadays, they are called Latin squares and orthogonal Latin squares. So let me explain what a Latin square is. Each of these 2 pictures, so this square here and this square here, is a Latin square. So what is a Latin square? In a Latin square of size n, you have n symbols, and these n symbols have to appear in each row and in each column exactly once. It's a very simple kind of thing, right? So in this one, all the chess pieces appear in each row and in each column, and it's very easy to make lots of different kind of Latin squares. That's very easy. The thing is, here you have one Latin square and here you have another Latin square, one of colors and one of chess pieces. Now the thing is, when you merge the 2, then you get the picture in the previous, what we saw on the previous slide. Sorry. So this picture is obtained by merging those 2 Latin squares. Of course, it will have every color once in each row and column, and every chess piece once in each row and column. But what is special about this is that each piece occurs 5 times in all 5 colors. Each chess piece occurs in all 5 colors. That's what is special. And that is when 2 Latin squares are said to be orthogonal. So these two Latin squares are orthogonal Latin squares. When you combine them in the way that I have described, you will have each one occurring as many times as the n. For in this case, n is 5. So Euler's question therefore is, does there exist a 6 by 6 pair of orthogonal Latin squares? That's the mathematical phrasing of that question. Okay. So let me begin with a brief history. So as I said, that is Euler's question, roughly 1780 in St. Petersburg. That's where it arose. And Euler himself answered it in some cases. So he showed that if n is odd or if n is a multiple of 4, then there exists a pair of orthogonal n by n Latin squares. That is for odd n or for n divisible by 4. So that leaves out all the others which are even and not divisible by 4. That's the sequence 2, 6, 10, 14, 18, 22. For all of these, we don't know the answer. At least he didn't know the answer, and he conjectured that there do not exist any such pair of orthogonal Latin squares for these numbers, for n a multiple of 2 but not a multiple of 4. And it's very easy to see that when n is 2, you cannot find a pair of orthogonal Latin squares. You just scribble on a piece of paper and you'll see very easily that you can't find orthogonal Latin squares for 2. And the next case, n equal to 6, is the case that he was asked, and he had an intuition that it's not possible, but he couldn't prove it. He couldn't quite prove it. He just said that, as he conjectured, it's not possible for any of those. So this problem has an Indian connection. So I'll come to that. So in 1900, so that's a good 120 years after the problem was posed, a French amateur mathematician, he was a French civil servant, Gaston Tarry, he showed that Euler's conjecture is true for n equal to 6. That means you cannot find a pair of orthogonal Latin squares of size 6. And this involved quite horrendous computations running into thousands of cases, but he did it, and this is considered to be the first proper proof that it's not possible, that Euler's conjecture is true for n equal to 6. Then about 50 years later, Bose and Srikhande showed that Euler's conjecture is false for n equal to 22. So they constructed a 22 by 22 pair of orthogonal Latin squares. So they constructed for 22 by 22 a pair of orthogonal Latin squares. And a little later, a year later or something, so Bose, Srikhande and Parker, they showed that Euler's conjecture is true only for n equal to 2 and 6. That is, 2 and 6 are the only things for which you cannot construct a pair of orthogonal Latin square. For all other values of n, they always exist. So Euler's conjecture was quite spectacularly false, right? Except for the first two cases, all other cases it's false. Okay, so now we know that the conjecture is false. So for 6, we really cannot solve the original problem that Euler considered. So what do we mean by a quantum solution then? What is meant by a quantum solution to this problem? So yeah, so let's look at the passage from classical to quantum. Typically in physics, when we first encounter something like quantum mechanics, the thing that arises is discreteness out of continuity. So the energy of the electron is quantized. It takes only certain discrete values. Here we are going quite in the opposite direction. What we are going to do mathematically is, we begin with a finite set. So this is a set of D elements. So we want to replace this set by a Hilbert space or an inner product space of dimension D, or rather just a set of unit vectors in that space, but let's not get technical. So we want to replace this set by a vector space with a basis of D elements, and on the set of symmetries of this set forms the symmetric group sigma D, and this naturally will get replaced by the symmetries of an inner product space of dimension D, which is the unitary group of D by D matrices which are unitary. And distinct here will correspond to orthogonal there. That is, two vectors which are orthogonal that's the analogy for distinct elements of this set. And an example of this is when D is 2. So you have a bit takes two values, 0 or 1, and in quantum computation a qubit is a unit vector in a two-dimensional complex space. That is, the topology of that is the topology of the sphere S3, but never mind. So all of these have, this is a rough dictionary between classical to quantum. So here is a Latin square. This is a Latin square of size 4. This is a Latin square of size 4. All the numbers 0, 1, 2, 3 occur in each row and column. So what would we mean by a quantum Latin square, QLS? So that is that QLS in the title over there. What is meant by a quantum Latin square? A quantum Latin square is a square, and every element of that square is a vector. It's a unit vector, and the rows should be orthogonal and the columns should also be orthogonal. So there's a very easy way of constructing from a classical Latin square a quantum Latin square by just taking, for 3 you take the third basis element, for 1 you take the first basis element, and this will give you quantum Latin square. But there are many more quantum Latin square than this construction can supply. Not all quantum Latin square are classical, right? So there are many more such objects. So now we get to what would we mean by a quantum orthogonal Latin square. That's what we want, a pair of Latin squares which are orthogonal. What does this correspond to? In order to explain what this corresponds to, I want to discuss 2 operations on matrices. So let us say a 9 by 9 matrix. We actually have to deal with 36 by 36 matrices, but for illustration I'll just deal with a 9 by 9. Take a 9 by 9 matrix and divide it into blocks of size 3 by 3 each. And I want to describe 2 operations. One of them is a very simple operation. It's called partial transpose. So this operation is the so-called partial transpose operation. You take each one of these blocks and transpose the block, right? You take the transpose, that is, you reflect about this diagonal. So in each of these blocks you reflect about the diagonal, you will get another new matrix, and that's the partial transpose matrix. That's one. Then there's another operation called realignment sometimes. In realignment, what you do is you take each block of this matrix and write it down column wise. So 1, 4, 7, 2, 5, 8, 3, 6, 9. You make that the first column of your new matrix. Then you take the second one, the block below it, then you write its 9 elements in the second column, and so on. So these are 2 operations on matrices. This might seem, why would one want to do such operations? But it turns out that this forms the building blocks to whatever you can do to a unitary matrix of size d squared. These two operations. So a matrix is said to be a quantum orthogonal Latin square if this matrix originally should be unitary. After performing this realignment, it should be unitary, and after performing this partial transpose, it should be unitary. So it should satisfy unitarity in so many different ways, right? Such a matrix is called a QOLS, quantum orthogonal Latin square, or a 2 unitary matrix. Sometimes it's called a 2 unitary matrix. I don't really like the terminology, but that's the way it is in the literature, because these 2 operations, under these 2 operations it's unitary, besides being unitary on its own to begin with. Okay, so an example of a 2 unitary matrix of size 9 is given here, right? And the reason I have given this example here is that this is a unitary matrix, but it's much more than a unitary matrix. It's a permutation matrix. It has only zeros and ones as entries. All these blank entries are 0, and then you have these ones in these places. And this, you can do the realignment or the partial transpose. You'll still get permutation matrices, and they are also unitary. So this is a 2 unitary matrix, and the reason is the reason that these permutation 2 unitaries are important is they correspond with orthogonal Latin squares of size 3, right? It's a 9 by 9 matrix, but it corresponds to pair of orthogonal Latin square of size 3. So if you want a quantum solution to Euler's problem, what we are looking for is a quantum orthogonal Latin square of size 36. So we want a 36 by 36 matrix, which should be a unitary matrix, such that when you realign it should be unitary, such that when you do partial transpose it should be unitary. So this was an open problem in this quantum computation community for a while, and until it was solved. And this solution received quite a bit of attention even in the popular things like Quanta magazine and things like that. So this is 36 entangled officers of Euler, quantum solution to a classically impossible problem. So these two of my co-authors, Suhail Radha, Arul Lakshminarayanan, and 4 Polish physicists, so gave the solution, whose names I think I'll not pronounce. It might be difficult for me to do that. So they solved this problem, and by explicitly constructing a 36 by 36 QOLS, quantum orthogonal Latin square. So let me just show you how that looks. So look at that matrix over there. All the blank entries are 0, right? You can see it's a very sparse matrix. There are 1296 squares over there, and most of them are blank. 112 of them have entries. And of the 112, some are blue, some are red, some are green. And what do this blue, red and green represent? Red represents a complex number with modulus this value. Green represents a complex number with this modulus, and blue represents a complex number with modulus 1 over square root 2. And this is not, this doesn't give you complete information about the matrix. Since I've only given you the moduli of the complex numbers, there is still phase factors. So there are phase factors which have to be very carefully fudged in order to make this into a QOLS. But this is what they succeeded in doing. Okay. So now let me get to asking whether that's the only solution or whether there are more solutions. So we would want to know, if you're given two quantum orthogonal Latin squares, what distinguishes them, or when would you say they are different? Of course, you can say they are different if they are not equal as matrices. You can say they are different, but that's not a very good definition. So for example, let me just go back a couple of slides. So look at this Latin square. If I interchange two rows, or if I interchange two columns, or do any permutation of the rows or any permutation of the columns, it still remains a Latin square, right? Those are all kind of trivial modifications. So permutations here correspond to trivial modifications. And remember, according to this dictionary, this permutation group corresponds to the unitary group in the quantum situation. So somehow, whatever notion of equivalence you're giving should involve the unitary group. And indeed, that's what the definition is of equivalence. So we say that two matrices A and B of size d squared are equivalent. That means we want to think of it as representing the same solution if you can find unitary matrices x, u, y, v satisfying this equation. And this equation can be pictorially represented by this picture. I'll explain what this picture is a little later. Let me just see how I'm doing on time. Okay, I'm almost done. Okay, so we want to be able to distinguish these solutions in some way. In particular, we want to say when two solutions are different. Okay, I'll state the main theorems. So the main theorems that we've shown are the following. First, that if you take 9 by 9 two unitaries, I gave you one example of a 9 by 9 two unitary. There is only one LU equivalence class of such two unitaries. That means there's, for 3 by 3 quantum orthogonal Latin squares, there is only one, and that's the one that I showed you. Whereas this theorem 2 that says that as long as d is bigger than 3, for example for d equal to 6, which is the case we are interested in, there are infinitely many different solutions of size d squared. And that means there are infinitely many quantum solutions to Euler's 36 officer problem. This is what we showed. So, and how did we do this? There's very little time, so I'll try to not explain this pictorial representation. I just want to say something about this one though. This is the Ouroboros. It occurs often in many cultures. It occurs in art, and today, in many talks of today, benzene structure has occurred. As everybody knows, Kekule discovered the benzene structure after having a dream of a snake swallowing its own tail. As it happens, this Ouroboros is also important for us mathematically because it represents one of the most important invariants. So if you take a linear operator, these pictures all represent various kinds of numbers, and a linear operator where it swallows its own tail represents the trace of that operator. It's a very important invariant of that operator. Okay, so more generally, this theorem was proved with my colleague Sundar in 2004, almost 20 years back. So what we did was we tried to give conditions under which two operators or two sets of operators more generally are unitarily equivalent. And this is an if and only if condition for unitary equivalence. The first part of the theorem is very trivial. It's the second line which is the important line. These conditions are complete for equivalence. So we'll tell you, given two operators from a tensor product of vector spaces to a tensor product of some other vector spaces. When are these two equivalent? And these two are equivalent exactly when many of these pictures that you can build from these operators turn to give you the same number. For example, one such picture is what was illustrated at the beginning of the talk. So this is a picture that can be built out of these two operators S and T. You are allowed to use S, T and also the adjoint of S. If S goes from R to B tensor G, all of these are vector spaces. I have just represented them by colors. Then the adjoint operator S star will go the other way. It will go from B tensor G to R. All of these have pictorial representations, and closed pictures that you can form from these evaluate to numbers. If all of these numbers are equal, then the operators are linearly equivalent, are unitarily equivalent, otherwise not. Okay, so I wanted to say a word about the proof, but I don't think there's enough time for that. I'll stop here. Thank you.
So it was a lovely talk, but there was some step in between which I think I missed. If I can just ask you,
Sure.
You discussed classical, what you called orthogonal Latin squares,
Yeah.
and then you squared the size of the square
Yes.
and
Yes.
defined a quantum.
Yes.
But I didn't see the connection. In the
Yeah, the
quantum
connection
case,
is-
there was some two operations that are supposed to.
Yeah, why
present-
squaring? So the reason for
Yeah.
squaring is if you take a QoLS of size 9, which I illustrated, and so each one of those square blocks had an entry. Only one entry was 1, all the other entries were 0. So for example, in the first block, the 1, 1 entry was 1, in the second block, the 2, 2 entry was 1. So if you write down this 1, 1, 2, 2, 3, 3 for this entire thing, you'll get a 3 by 3 matrix, and that's actually a pair of 3 by 3 orthogonal Latin squares.
You get one 3 by 3 matrix,
Yes.
or a pair of, then how? Oh,
Because you'll write down both the row and the column numbers. So the row numbers will give you 1, the column numbers will give you 1.
I see.
And together they'll form a pair of orthogonal Latin squares.
I see.
So that is why the squaring occurs.
And the use of the word quantum, I thought you were going to take linear combinations of since you introduced Hilbert space, I thought you.
In a sense, yes, we are taking linear combinations because all of those things involve very complicated kind of
operations on the vectors. I see.
They are not simple basis vectors. They are complicated linear combinations of the basis vectors.
I see. Thanks.
Does your description hold for decimal numbers only, or can be
Hold for sorry?
extended to bits and applied to cryptography?
I don't know what kind of application. There is something called quantum cryptography. I don't know much about it. So I don't understand the question. Sorry.
No, the first part, at least the first part.
The first part is meaning?
The number system is just 0 and 1.
No, the number system doesn't really matter. It's just a finite set. You could do it for any finite set. 0 and 1 is just a choice. You could do it with 3, for example.
Okay. Then one can think of cryptography, data and encryption.
It's possible, but I don't know that.
Okay.
As I understand, Euler conjecture, there is no solution.
Yes.
And you call it a classical solution.
Yes.
And what I understood from the wonderful presentation by you, very crisp, very nice mathematics, there is a quantum solution,
Yes.
infinite number of quantum solutions
Yes.
for this problem.
Yes.
Now, even though I'm familiar with some differential equations, classical solution and non-classical solution and all that, what exactly is the difference between a classical solution to the Euler conjecture problem and the infinitely many non-classical
Yes.
quantum solutions to the problem?
Yes.
What I want to know is there a measure of discrimination between a classical solution, yes, there is some number, and there is a quantum solution, there is another number, and the difference is infinite, or something like that? What is it? How do I hold your solution
There are,
in my hand?
Yeah, there is a very precisely defined notion of what a classical solution is and of what a quantum solution is. So in a way we are getting around Euler's problem by redefining what we mean by solution. So what was originally meant by a solution was a classical solution, which essentially means a permutation matrix of a certain size satisfying certain properties. But now we have said we are not looking for permutation matrices. Let us generalize the class of matrices to unitary matrices which satisfy certain natural properties, and there we can find solutions.
That means you are departing from the starting point of Euler's statement. Is that the case, or what exactly is that?
In essence, yes, because we know Euler's original problem has no solution. We know that. So we are.
It is as though you reformulate a problem and come out with infinite solutions. Is
Yes.
that the case?
Yes.
Oh.
But it's a very natural reform.
No, that's
I mean, one can do it, it has to be done tastefully.
Remarkable. I admire your presentation.
Thank you.
The thing is, in Sudoku, there are some sort of similar problems associated.
Yes, there is a quantum Sudoku also.
Oh,
There is a quantum Sudoku.
My hearing is bad, that's why I couldn't get to know. But whatever you have presented is absolutely beautiful. I admire your presentation. The thing is, I wanted to see where do I hold this. That means it is as though I don't have a solution to old problem. I will give you a modified problem for which I have infinite solutions.
That's
is that
true.
the case?
That is correct.
Thank you very much. I'm
That's
grateful
correct.
to you.
Thank you for a really lucid presentation. I just had one continuation to the question that the professor asked there,
Yes.
that the classical solution would actually be a special case of the quantum solution, right?
Sorry, what?
Would you get the classical solution as a special case of the quantum solution that you got here?
Will we get what?
The classical solution to the Euler problem,
Yes.
wouldn't that be a special case?
That
the
would be a
quantum
special
solution?
case, but the classical solution doesn't exist in the 6.
Ah,
There is no
so
classical solution.
even though there are infinitely many quantum solutions, none of them in the limit
None of them,
gives
it's
you
not a classical solution. No classical solution exists. The point of this whole thing is the quantum solution exists. That was the really nice discovery by those physicists in early 2022. But now what we can see is it's not just one quantum solution. It's not an isolated thing, despite the fact that they had a lot of difficulty in finding exactly. You have to match parameters very carefully in order to be a quantum solution. Despite that, you can still find an infinity of quantum solutions.
At
That's
the
the
risk of
point of
asking a
today's.
slightly unfair question, this quantum solution is linear algebra or is it numerical, or very roughly, what was the method that helped you to converge onto the solution?
You can say it's basic linear algebra.
Right. Okay.
It's
Thank you
basic
so
linear
much.
Very
Yes.
quick question if you have.
Yes.
Will there be an infinite number of quantum solutions always?
In fact, one of the that's a good question. Thank you for asking that. In fact, for one of the cases, we started with a classical solution and then modified it by changing phases to produce an infinity of quantum solutions. That's not always possible, but in one of the cases, it is possible, and that is how we did that.
Quick question here at the back. Very nice talk. So actually I have two questions. One is more of a quick clarification.
Okay.
So the popular Sudoku puzzles are technically a Latin square, right?
Yes,
Right?
they are. They are more than a Latin square, because there are conditions even on the 9 by 9s, small ones. It's more than a Latin square.
Okay, all right. And the second question is sort of a lazy one because I should probably go read that PRL paper, but anyway, I'll ask you. So it sort of follows from the question that came earlier.
Okay.
So for the particular solution that Arul and co-workers had constructed last year, so was there an algorithm that they devised to search for this solution?
Yeah. They could see how they got it. They did a lot of computer work.
Okay.
And then they slowly converged on something which seemed to be a solution. Then they did it exactly, and rather very nicely, the golden ratio is involved in their solution. It's an exact, their solution is an exact solution. It's not a numerical one, it's an exact solution, and the golden ratio is involved in this construction.